Now, I'm a practical chromatographer. I'm not a theoretician. I'm not big into equations, but this is something that it's going to make your life easier if you understand this. So the resolution equation, every LC, GC, SFC, any kind of chromatography in the world follows this equation, and that is in order to get resolution, and that's our goal to separate peaks, we have three things. We have capacity factor, we have selectivity, and we have efficiency. So just mathematically, if you look at this, it says, okay, I get it. If I want to get a good separation in LC, I need to have three things. I need capacity factor, I need selectivity, I need efficiency. The bigger these are, the bigger this is, the better the resolution is. So we have rules, guidelines as to what these numbers should be. Instead of just tossing you out into a vacuum saying, there's the equation, you guys go figure it out, we look at it, we say, well, capacity factor, just considering the fact that it's K over 1 plus K, if we were to graph, let's see if we can do this. If I were to graph capacity factor versus resolution, it looks like this. It's literally 0 at the beginning. It's really, really steep, and then it starts to plateau out. So what does this tell you? If we want good resolution, now if I want the highest resolution possible, I would want the highest K possible, and that would take an infinite amount of time to do chromatography. Doesn't make much sense. But if you look at this curve, you're like, well, infinite would be great, but boy, I could get to 50% of infinite with a capacity factor of 1. And I got 2, 3, 4, 5. So what this says is, if your capacity factor is low, put all of your efforts into making it better. How much better? Well, 1 is a lot better than 0.5. 2 is better than 1, 3 is better than 2. Is 5 better than 4? Yeah, a little bit. Is 6 better than 5? Yeah, a little bit. So you get the idea that that's where this number comes from. We look at that, we say, if you've got a capacity factor of 1, 1 over 1 plus 1 is 2. So 1 over 2 means this number is 0.5. You're halfway to the ultimate number, and it only took a few minutes. So that's where capacity factor of 1 comes from. So we say capacity factor should be between 1 and 5. And you understand this is not an exact number that you're going to fall off a cliff, but what it tells you is if you're less than 1, you're sacrificing a lot of resolution. You spent $75,000 to buy that LC, and you're throwing 90% of it away because you're impatient. So this says, hey, just back that off a little bit, get a good capacity factor, get a good resolution. So that's where that number comes from. Selectivity. I know the question was in there. So we always say alpha should be greater than 1.2 for LC, for Pat columns. 1.05 for GC, for Kepler columns. I look at this as a very empirical equation. And I look at it this way. We have efficiencies. We know what these numbers are. In LC, we get 10, 20, 30, 35,000 plates if we're really, really lucky in LC. So in order to get resolution of 1.5, that's our goal here, is resolution greater than 1.50. So if that's our goal, we know that capacity factor tops out, right? Once you get this term to 1, it doesn't get any better than that. We know efficiency in LC. We can get 30,000 plates, but we don't have 300,000. Sorry, not going to get it in LC. So I believe selectivity really comes from that back calculated, saying, you know what, in LC, you better have chemistry. You better have enough chemistry to give you a 1.2. I look at that as, to do 20% of the separation, you better have some chemistry, and we'll take care of the rest with our skinny peak thing. In GC, it says, hey, we have so much efficiency. GC, you could buy a 400,000 plate column off the shelf. I got so much of this, I don't need very much chemistry. I only need 5% of your chemistry, 1.05. I need a little bit of chemistry because I got a great big giant sledgehammer here. So, taking a big step back, where do these numbers come from? Resolution equation is empirical, which is great, which means it actually matches the data, and it gives us the ability to predict this stuff. So capacity factor, simple. You just get it above 1. 2, 3, 4, 5, fantastic. Don't try to get it from 10 to 20 to 30. I can show you how to do it, but no benefit to doing that. And selectivity, this is the chemistry. This in LC, this is your stationary phase, C18, cyano, amino, diol, and versus the mobile phase, methanol water, acetonitrile water. We have the master resolution equation, this thing. we also have what's called the graphical resolution equation. So graphical resolution means, okay, I've got two peaks. Are they separated? Is there baseline in between them? So it has to do with how far the peaks are at the top versus how broad they are at the bottom. So if I say I've got two peaks a minute apart, is it good or bad? Well, if the peaks are 5 minutes wide, a minute apart, no, that's bad. If they're 10 seconds wide, a minute apart, that's good. So what you want to know is how far the tops of the peaks are apart versus their average width at base. So we have this equation that says delta T, so the difference in retention time, divided by the average width at base. So here's how I like to do it. The width of peak 1 plus the width of peak 2, and then half of that. So right, so it's the average of the peaks, peak widths divided by the difference in time. So that sort of says if we get two peaks that are just barely separated, that would equal 1.50. So it really is a mathematical equation, a graphical equation, literally like, yeah, I got these two peaks. How much space do I need in between them to separate them? And it's like, well, how broad are they? So that's why resolution takes into account not just delta T, difference of retention time, but difference of retention time versus the peak width. So that's where the 1.5 comes from. This resolution is the same as this resolution. So R is R. That's how we measure it. That's how every software system in the world measures your resolution. This is how we affect it. This is how we change it. This is how we improve it.